a previous Pope wrote the shroud was, quote, a truly mysterious image which no human artistry was capable of producing, Lara. But we have the book, the broadcast, and now the app.
For nearly 2,000 years, a single artifact has captured the imagination of billions. It sits behind bulletproof glass in the Cathedral of St. John the Baptist in Turin, Italy. A length of linen cloth measuring 14.5 feet long by 3.5 feet wide. Faint upon its surface lies an image, the front and back of a male figure bearing the wounds of crucifixion. Scientists have called it a medieval creation. Believers have called it divine. But neither camp was prepared for what would happen when artificial intelligence turned its attention to the cloth. What the algorithms found wasn't proof of authenticity, nor irrefutable evidence of forgery. Instead, they uncovered something far more puzzling, a pattern of order that shouldn't exist at all. This is the story of how machines saw what human eyes had missed for centuries, and what that discovery means for one of history's greatest mysteries. The Shroud of Turin presents a paradox. It is simultaneously the most famous cloth in Christendom and the most contested. Its documented history begins in the 14th century in a small village in France called Lire, where it was displayed as a pilgrimage site. Almost immediately, controversy erupted. In 1389, Bishop Pierre d'Arcis of Troyes sent a letter to the antipope claiming that an artist had confessed to forging the shroud as a tribute to the crucifixion. The Vatican's response was cautious and ambiguous, allowing its display while requiring that it be announced as a representation rather than the authentic burial cloth of Christ. Over centuries, the shroud moved through the hands of nobility, narrowly escaped destruction by fire, and eventually found its way to Turin in 1578. The cloth became the most intensely studied religious artifact in history. By the 20th century, no object outside of scientific laboratories had received more rigorous examination. The turning point came in 1898. A lawyer named Secondo Pia received permission to photograph the shroud. When he developed his negatives in a makeshift darkroom, he made a discovery that would transform the entire conversation. The faint image on the cloth appeared with startling clarity when photographed as a negative. The subtle markings became a clear portrait. The feature that had been barely visible to the naked eye suddenly possessed depth, definition, and anatomical precision. This revelation was explosive. If the image behaved as a photographic negative, it suggested properties that conventional artistic techniques couldn't explain. How could a medieval artist have created a negative image 400 years before photography was invented? The question hung in the air, unanswered. By the 1970s, a team of scientists had assembled to conduct the most comprehensive examination of the shroud ever attempted. The Shroud of Turin Research Project, known as STURP, was organized by John Jackson and his colleagues in 1977. In 1978, a 32-member team traveled to Turin and spent 120 hours examining the cloth with every technique available at the time: X-ray fluorescence, spectrophotometry, infrared analysis, ultraviolet photography, and microscopic inspection. What emerged from their work was a detailed inventory of puzzles. First, the image showed no evidence of paint, no binder layer, no pigment particles buried in the fibers. The discoloration appeared to sit only on the surface of the outermost fibers, a superficial yellowing measurable in mere microns. This raised an immediate question. What process could create such extraordinary pictorial detail while leaving almost no chemical trace? Second, the image possessed what researchers called three-dimensional information. The intensity of the image appeared to correlate with the distance a body would have been from the cloth. Where the cloth would have touched closely, the nose, the forehead, the cheekbones, the image was darker. Where it would have been farther away, the image faded. This wasn't artistic shading. This was geometric mapping. Third, the blood-like stains behaved differently from the image. They had penetrated the fibers deeply, staining the threads from core to surface. The image had not. This suggested two separate processes, occurring at different times or under different conditions. STURP's final conclusion, published in peer-reviewed journals, stated that the image was not the product of an artist, as it was difficult to explain through any known medieval technique. Yet this conclusion was more a statement of puzzlement than of certainty. The shroud had simply resisted every category researchers tried to place it in. In 1988, an attempt was made to settle the question definitively. 3 internationally recognized laboratories, the University of Oxford, the University of Arizona, and ETH Zurich, received small samples of linen cut from a corner of the shroud. Using accelerator mass spectrometry, they measured the radiocarbon content and published their results in the prestigious journal Nature. The verdict seemed conclusive. The shroud dated to between 1260 and 1390 CE. Headlines around the world proclaimed the shroud a medieval forgery. The mystery, it seemed, was solved. But the solution created new mysteries. The samples had been taken from a corner of the cloth, an edge region that had endured centuries of handling, multiple repairs, and damage from a documented fire in 1532. Textile historians and chemists soon began questioning whether the sample site was truly representative of the whole cloth. In 2020, a team led by P. Di Lazzaro and colleagues published a statistical analysis in the journal Entropy of the raw data from the 1988 tests. Their findings were startling. The subsamples showed non-homogeneous results, suggesting they had come from fabrics of slightly different ages. More troubling still, there was a systematic linear relationship between the apparent age and the position of the subsample within the original cloth fragment. This kind of spatial variation is precisely what you would expect if the sample contained later material introduced during medieval repairs, not what you would expect from a uniform, original cloth. The researchers concluded that the 1988 radiocarbon dating does not match current accuracy requirements. The case that seemed closed had reopened. By 2024, the shroud had collected decades of high-resolution photographs and multispectral images. Researchers had documented its appearance in ultraviolet light, visible light, infrared wavelengths, and combinations thereof. Enormous databases of pixel information existed, far more data than any human researcher could meaningfully process. Yet all of this data had been examined with human cognition as the limiting factor. Scientists looked for patterns their eyes could see. They sought to explain anomalies their minds could conceptualize. But pattern recognition at scales invisible to human perception, the kind of structure that emerges from thousands of data points, remained invisible. This is where artificial intelligence entered the conversation. In June 2025, Dr. Thomas McAvoy, a chemical engineer at the University of Maryland, published a peer-reviewed study in the International Journal of Archaeology that applied machine learning algorithms to multispectral images of the shroud. His approach was methodical and carefully constructed to avoid bias. Rather than asking the algorithm to identify a face or confirm existing theories, McAvoy used principal component analysis, PCA, a technique that mathematically separates variants in data to reveal hidden structure. He applied this to both visible light and ultraviolet-induced fluorescence images of the shroud, allowing the algorithm to identify which aspects of the data contained the most information. The results were striking. According to McAvoy's analysis, the vast majority of information in the ultraviolet fluorescence images could be explained by a single principal component that correlated directly with raw pixel intensity. This meant that the pattern wasn't random noise or artistic variation. It was ordered. It followed a rule. More significantly, McAvoy's analysis suggested that the pattern behaved as if it had been created by radiation rather than by conventional techniques. The researcher noted that the intensity variations across the shroud surface, combined with the superficial nature of the discoloration, were more consistent with some form of energy event than with painting, transfer, or contact alone. McAvoy was careful not to overstate his conclusions. AI detects a radiation-like signal, the headlines proclaimed, but the researcher's own language was more measured. He had identified patterns in the data that resembled mathematical models of radiation effects, but he acknowledged that the mechanism remained unknown. The revelation prompted other researchers to test whether AI could be fooled by simpler explanations. If the shroud were simply a painting, would AI recognize something different? If it were a contact imprint, cloth pressed against a body, would the patterns hold up? These adversarial tests became crucial. Researchers applied the same analytical techniques to control samples, linens that had been subjected to heat, staining, or transfer of pigment from relief sculptures. In every case, the patterns differed from what appeared in the shroud's image. A particularly important study came from Cicero Morais, a digital graphics expert from Brazil. Using sophisticated 3D modeling software, Maurice created virtual experiments where cloth was draped over both a full human body model and over shallow relief sculptures. The question was simple. Would fabric resting against these different forms produce an image matching the shroud? When cloth was draped over a full human body, distortions appeared around the shoulders, cheeks, and fingers, exactly what physics predicts. The image would be warped, wider, misshapen by the volume of the body beneath. But the actual shroud showed none of these distortions. The proportions were relatively undistorted, as if the cloth had recorded not a direct contact, but a distance-mapped relationship. When Maurice tested fabric draped over a shallow relief sculpture, the results improved, but still didn't match perfectly. The conclusion was important. If the image is real, neither direct contact with a body nor simple contact with a sculpture explains its properties. Parallel to the AI research, other laboratories were exploring non-destructive dating methods. Dr. Liberato De Caro and his team employed wide-angle X-ray scattering, WAXS, to analyze cellulose degradation in the linen fibers. This technique measures the crystalline structure of cellulose, the primary component of plant fibers, and uses that as a proxy for age. Unlike radiocarbon dating, WAXS doesn't require destroying samples. It can provide information about natural aging by examining how cellulose crystals have degraded over centuries. The initial results suggested ages that, in some trials, tended toward an earlier date than the 1260 to 1390 CE range established by radiocarbon dating. Critics argued that humidity, heat, and storage conditions could alter the signal, but supporters noted that every dating method carries sensitivities and that convergence across techniques matters more than any single measurement. The picture was becoming complex. Radiocarbon dating suggested medieval origin, but with serious methodological questions. AI analysis suggested patterns consistent with radiation. Alternative dating methods pointed toward earlier origins. None of these findings were definitive, but together they suggested that the 1988 dating verdict had been premature. As research teams analyzed the shroud more carefully with computational tools, a new category of findings emerged. Beyond the obvious image of the figure, subtle patterns appeared. Patterns that required transformation and spectral analysis to become visible. When researchers layered images from different spectral bands and subjected them to various computational transforms, they noticed something unsettling. Faint symmetries appearing around parts of the face and chest. These weren't the symmetries you'd expect from fabric folds or camera artifacts. They persisted across different analytical methods. They survived the removal of noise. They appeared even when researchers randomized regions to serve as controls. The response from skeptics was immediate and reasonable: confirmation bias. Machine learning systems are notorious for finding faces in clouds, patterns in toast. To avoid this trap, researchers used neutral analytical techniques, mathematics that didn't contain any preloaded assumption about what should be found. Even using these purely mathematical approaches, the structure remained. The conclusion was cautious but important. The shroud's image is not unique in containing subtle patterns, but it is different from control samples in the consistency and nature of those patterns. Perhaps most intriguing was the interaction between the image and the blood-like stains. One might expect that chemical analysis of the stains and chemical analysis of the image would show similar properties. Instead, the opposite appeared to be true. The blood-like stains seemed almost irrelevant to the geometric order researchers were discovering. The mathematical patterns that characterized the image continued beneath the stains, indifferent to added layers. This suggested something profound. The image and the stains were created by separate processes. This raised questions that previous researchers hadn't adequately addressed. Did one event mark the cloth chemically while another etched its geometry into the fibers? Or does the cloth record two overlapping but unrelated histories? If the bloodstains came from contact with a body, and the image came from a separate process, whether radiation, chemical reaction, or something else entirely, then the shroud is not simply a record of a single event captured in fabric. It is a palimpsest, a cloth that has recorded multiple events or processes. One of the most consistent findings across all research methods was the extraordinary superficiality of the image. The discoloration appeared to sit only on the crowns of the outermost fibrils, the tiniest structural units of the fabric. Depth maps built from intensity variations consistently showed the same pattern. Color change confined to microns, not penetrating into the core of the fibers. This posed a specific technical challenge. Multiple attempts by independent researchers to reproduce such a shallow, uniform effect on linen had failed. Laser experiments produced results that were close, but not exact. Heat methods worked too deeply. Chemical processes either didn't penetrate far enough or diffused too broadly. Ultraviolet light could burn the fibers, but it left different characteristics than those observed in the shroud. What process could impart energy so precisely that it altered only the top of the outer fibers, and did so in a gradient that tracked distance from a theoretical body surface? The question remained unanswered, but it increasingly seemed that no known technique could explain it. As evidence accumulated, researchers began to grapple with interpretation. If the image is an accident of contact with a body, we should see disorder, distortion, the random marks that physical contact produces. We see instead mathematical order. If the image is artwork, we should see tool marks, evidence of human technique applied across the surface. We see instead a superficiality that defeats conventional artistic methods and a three-dimensional mapping that suggests something more like a projection or a radiation effect than a brush. If it is neither accident nor artwork, then we have encountered a process for which we possess no contemporary explanation. The physicist who led one analysis put it plainly in private correspondence. This does not behave like an artifact. It behaves like a phenomenon. A critical distinction emerged in how different researchers framed their questions. The radiocarbon dating had focused on when, on establishing identity and dating. AI analysis had shifted the focus to how, to understanding the mechanism and nature of the process. These are not equivalent questions. The radiocarbon dating established a date range, subject to methodological objections, but it never addressed how an image with these specific properties could be created, whether in the medieval period or any other time. AI analysis, by contrast, had little to say about dating. The algorithms couldn't tell you whether the cloth was 200 years old or 2,000, but they could tell you something crucial about the nature of the pattern. It follows rules. It exhibits order. It behaves as if governed by a physical law rather than created by artistic intent. Theologically, this distinction matters. Believers had often pointed to the shroud as proof of resurrection, of a unique, miraculous event. But scientists had argued that miracles, by definition, exist outside the realm of scientific explanation. If the image formation mechanism is unknown but potentially knowable, then the question moves from theology to physics. The shroud becomes not proof of divinity, but a puzzle to be solved. Yet solving it might prove harder than establishing a date. Throughout this period, the Vatican maintained public silence. The Holy See has never claimed the shroud as authentic, and as with all relics, makes no definitive statements about its nature. Church custodians were well aware that any pronouncement would be weaponized by both believers and skeptics. Better, they seem to have concluded, to let the data speak. Behind that public silence, however, conversations continued. Researchers were permitted to study the shroud within strict constraints. No further radiocarbon samples would be taken. The custodians had been burned by the methodology of 1988, but non-destructive analysis was allowed. Photography in different spectra, computational analysis of existing images. The door to investigation remained open, but carefully guarded. For scientists involved in the research, the AI findings had created a strange kind of dread. Not the dread of discovering something supernatural. Science is equipped to be skeptical of such claims. Rather, the dread of encountering something that refuses to fit existing categories of explanation. Terrifying was the word researchers used privately, but it meant something specific. It meant category breaking. It meant that the more carefully they measured, the less the shroud resembled anything they knew how to classify. It wasn't clearly an artifact or clearly a phenomenon. It wasn't clearly a tool or clearly a law of nature. This kind of intellectual uncertainty is profoundly uncomfortable for scientific methodology. Science prefers to sort before it measures, to place things into known categories, then study properties within that framework. The shroud asked for the opposite. Measure first, establish what the properties actually are, then attempt to sort it into a category, if one exists. As AI research on the Shroud continued into 2025 and beyond, new questions multiplied. Does the geometric pattern appear uniformly across the entire image? Does it weaken near the limbs? Does it follow thread direction or ignore it? Could advanced microscopy confirm whether the superficial coloring appears consistently on fibril crowns everywhere? Or does it vary in ways that might suggest different mechanisms for different